Joining me on our very first lesson for dual enrollment pre-calculus. My name is Ms. Augsburger, and we have a very interesting way of going through things this year, but that's okay because we will get through this together. Here we go. So today we are going to be focusing on our very first chapter, very first unit, which is over functions. Now, functions can be all sorts of different things, and we're going to kind of go at this from kind of a really beginning level and slowly move our way on up. So the first thing that we're going to be talking about are what are relationships, or what are relations, identifying the domain and range of relations, determining whether or not a relation is a function, identifying functions as continuous or as discontinuous, and if it is discontinuous, being able to classify that discontinuity as infinite, jump, or removable. As we go through our lessons, note that all of these guided notes are available to you for download, and you are more than welcome to print them out and follow along with us, or you can just take the notes on your own paper. But here we go. What, in fact, is a relation? Well, a relation is any set of ordered pairs. And for us, we're going to deal with ordered pairs of being something, for example, as the set of the points. I don't know, we can really say whatever we want. 0, 2, the point 2, -3, the point 4, 4, and the point 8, -6. Oops, helps if I write the 6 if I'm saying 6. And when I'm doing this, I'm using set notation, and that's very, very important. For example, these squiggles, they're called braces. They group together all of my ordered pairs to define a relation. And basically, this relation is a mapping, can be represented in table form. If you're doing this in table form, understand that for right now, at least, we're going to be talking about X and Y, where X is my independent variable, Y is dependent. So if I take this same ordered pairs, I could think about that as 0 pairs with 2, 2 pairs with -3, 4 pairs with 4, 8 pairs with -6. You can do as many different types of pairings with these as you'd like. It is just the fact that this is another way of writing that same thing. Now, when we're talking about a mapping, that's generally just saying, okay, if I have, I'm going to be fun and use my awesome tools. If I have two groups, there's my first group, here's my second, and I'm going to map, let's go ahead and stick with the same numbers that we've been talking about. We have 0, 2, 4, and 8 are in my independent variables. -6, -3, 2, and 4, those are my dependent variables. And this mapping is the same thing as describing those functions as 0 maps to 2, 2 maps to -3, 4 maps to 4, and 8 maps to -6. So that's a mapping where basically you're saying this group is my X. It's indicated by the fact that there's no arrow on this side. It maps to my arrow, my Y values. I can do the same thing if I would like with a graph. And just because those are some funny numbers, I am going to go ahead and just make up my own graph here where I have an X axis and a Y axis. Please make sure you always have something that indicates your scale if you are drawing an axis. You don't need to have every single number written down, but you do want to have at least enough to set and establish a scale. So I'm going to just say my graph, I can do coordinate points like this. If I'd like, I can even connect points with lines or other shapes. That's also a relationship, because again, a relation is talking about a mapping of X, my independent variable, to Y, my dependent variable. And we're all quite familiar with what the equations look like. When we talk about equations, what are those? Well, an equation is just something along the lines of y equals negative 3x squared plus 7. And these are just one example for each of those different types of representations that you can have. And within each, there's an infinite number of choices. So when we do this, what do each section represent? Well, first we have the domain. The domain is going to be the set of all x values. And so for my domain here, if I wanted to go back through, I could say the domain is the set 0, 2, 4, and 8. And that is the same thing for 2 and 3. For 4 and 5, these guys are continuous functions, so they're going to have a full range, and so those domains are going to be a little bit different. But no matter what, when we're talking about domain, we are talking about the x values, whatever they might be. And we typically like to put them in numerical order, just because it keeps us kind of understanding what's going on. So my domain is the set of all x values. We're discussing the range. The range is then the other side. The range is the set of all y values. All of the dependent values, everything that we get after we put our range into our domain into the function. So that means the range is going to be the second portion of all of these. The range is determined at the y-axis. And if I were to write my range, for example, for the first 3 problems, I would say the range is the set to negative 6. I'll take a moment just to kind of point out to you guys that when I'm listing just values, just numbers, I don't put those parentheses. Those parentheses are very important because they establish something as an ordered pair. So be careful with that. All right, so those are the general idea of relations. So what we're going to do, since when we talk about domains and ranges, we often talk about writing them in interval or set notation, you need to be familiar with how to do this. Now we have 2 different choices. We have a choice of using interval or set notation. I'm going to be focusing primarily on set notation. So for set notation here, if we look at this graph, we see that my graph starts at 3 and it continues on to infinity. So that means that my domain for this guy is the set of the numbers from 3 to infinity. But we have to think about what values are included and what values are not included. If we see here, 3 has a closed circle. Closed circle, if you recall, is denoted by a bracket. That says I'm going to include that value. Now, if you think about it, you never truly reach infinity. So since I can always keep going further and further out, I'm going to put a parenthesis on that, and that means that it does not include. It gets close as it possibly can, but infinity isn't a number that we can put our finger on. Because of that, we're going to use a parenthesis. So again, we see that when we're talking about something, if we have a closed circle, we use a bracket. Infinity, however, always has a parenthesis. And you must always, when we're talking about set or interval notation, go from the smallest value to the largest value. That is not an option. Okay, whichever symbols you use on those, you must go in that order. Now, for the next picture, what is covered? This gets a little bit confusing because if you look over here, I can see a thin line and a thick line. All I have here is a thick line. That tells me everything is covered or included in this set. So how do I write that in set notation? Well, for set notation, you have a couple of different choices. You can write the domain here as the set of all values such that every single one of those values is a real number. Okay, and some notations on this. Understand that this line here means such that, and sometimes you will see that written as a colon, just depending upon what's easier to type. I think the line is easier to write, but if I'm typing, I a lot of times to use the colon. The sideways E, so kind of, it's not a hard, it is just a C with a line through it. That means is an element of. Okay, so you can write like this, or also in set notation, you can use a little bit of an interval trick, which says that X is between, I'm not going to equal to sign because we're actually hit infinity, negative infinity, positive infinity. Again, always making sure that when you're looking at this, let me make this a little bit clearer here, that it always goes from small to larger. If you put a negative on this one and a positive on this one, even if you flip your signs around, you can't do that. That is not appropriate notation. You will be marked off for that. So I would actually stick with this guy. Left to right, and that was my whole motive behind that. Looking at number 8, how would we write 8 in set notation? First off, I need you to understand that we actually have two pieces working together here. We have this and we have that section, but they are separate. So I'm going to have to do something that tapes them together, and that is the union. That is what that U stands for. And so now I'm going to represent both of these pieces on either side of that U. So my negative infinity goes out that way, my positive infinity goes out that way. So when I do this, I say it goes from negative infinity, always going from small to large. I stop at -7. What symbols do I use on each of these? Well, I never reached negative infinity, so that is a parenthesis. I don't actually include 7, so that's also a parenthesis. Then you use your union symbol. What about the right-hand portion of this? How do I write that? Well, the smallest value here is 2, and it goes all the way up to infinity. I do include the 2, because that's a closed circle, but I never reach infinity, so that is a parenthesis. What about number 8? Can you do number 8? For number 8, looking at the left-hand piece, again, left and right are my infinities. So I am starting from negative infinity and go up through a positive 1. I know infinity, that 1 has an open circle, so it should be a parenthesis as well. Now I've got a break, so I'm going to union this together with its other piece, which starts at 5 to infinity. 5 also has an open circle, so it is a parenthesis, and you reach infinity. So while this section is called relations, the unit that we're on is actually functions. So what differentiates between a relation and a function? Well, a relation is a function, and this notation here, that guy right there, that means if and only if, and it is sometimes written with an equal sign with arrows on either side. That means I can go either direction. A relation is a function if and only if. Can anybody tell me what that is going to be? A relation is a function if and only if each element of the domain is paired with, and this is the key word here, this is very important, exactly one element. You might have heard that before. Each x has only one y. But we're going to be a little bit more generic in our definition simply because we're not going to be using just x's and y's. All right, so what does that mean? Let's put through context. If I look at number 10, I want to first determine let's determine the domain and range. So when I do this, because I'm two different sets, I'm going to mark each of them. The domain here is a set. So try to think, how would you write the equation of the domain on this? Domain is such that, and for this, I'm going to write x is -1, 7, 3, or 5. This can sometimes be written as just -3, negative. I kind of prefer, this is just personal and years and years too many math classes. Right method, this method is acceptable as well. You might come to a point where you're in a class and you have to identify the fact that the domain specifically involves the x values when you have different values. But for now, I'm okay with that. That's fine also. So that's the domain. This is the range. The range is the set of y such that y negative 0 that. You can say that as -0, 4, that's fine as well. Now, is that a function? Each x can have only one y. Each x's only show up once. I don't have x repeating itself in the domain. That tells me that this is a function. Now, for number 11, I'm going to tell you right now, this type of a setup represents the most missed question whenever we go over domain and range of functions or of relations. And that is because if you look at this, how are these numbers represented? I'll just take the shorter way out with this to get to that. The mean is my x, my independent variable. Either there's an x. All I'm doing is to the just look at coordinates. That means my 1, so that's -3, -1, 2. Domain. My range on the other end is talking about your values, your dependent values. And so that's going to right. So I see hit here. To right, I would hit here. would here and here. So for this one, range is going to be the points where the values, and I'm going to again start from the bottom, so that's 3, 4, -4, -3, and 5. One thing you cannot do, if you tell me go from -3, write it like that, whether you put right in that way alone, you will never write. And the reason why is that little piece in between, I don't actually have a point like with this, like with this, with here. I don't have any, so I have to be careful and make sure only points, the exact values that are on my graph. So, what do you think? Is this a relation? I want to determine whether this is a function. So I have a picture. The easy to do that is to do the vertical line test. So I'm going to drag vertical through my graph. Each where I hit along this x-axis with a y. So I'm okay there. I'm good here. And here's a problem. There, I have a value where the line crosses x once, coordinating y values. It is not a function. Because that vertical test is easy for us whether or not something is a function. When we're looking at this next one, actually more the same thing. It's very similar to number 10. Because back and we look at our examples of relations or tables, maps, those are all the exact same thing. So it's just understand what pairs with what. And this is actually even easier. For my domain, my domain is, remember, the domain is everything that's in your x or the start of each. My domain is what range be? 0, 1, 4. This, well, look, each one of my just has one line off. I can't do this all. And every value is one y. I don't have the notion. So just have one piece of it. This is what would the domain and range on number 13? When I'm about domain, at each point along the graph, x-axis. So I have a point here and 0 at the end forever. The domain is the set of x. When you do it this way, it's not just a list of points. You do have to use that notation. Such x is closed circle going to the right, greater than or equal to negative. For the y values for my range, do the thing right. This point collapses y right here. I can see that I'm going there. This is not going right. It's right. That means continue on forever. my set of lines such that I is a closed circle, so it's or equal to 1, 2, 3. Answer the question, is this a function? What do you think? This is a function. I look at my original value, I cross that graph exactly 1. So one more piece that we're talking about today, and that is continuity. A graph is said to be continuous if there are no breaks or holes in the graph. Basically, what I like to think of this is it's continuous. If you draw it without that needs to be continuous. I don't need to take it off page. It would go on and on and on. Technically speaking, it would go on forever, either to the left or to the right. There would never be a time for me to pick a pen in order to draw a graph. If there are breaks or holes in the graph, then that function is said, well, it's going to be continuous. And there are actually and discontinuities come and play a very large role when we get to calculus. Start using this called limits. So I felt like it might be a good idea to chuck this in here just so you have a chance of seeing it. Now, what we've got going, do you know this graph specifically at that value right there called? These are kind of discontinuity. We call these infinite discontinuities. And that's because as I get close to value, I come along, that's what it's saying. This is saying x and the sign, and this will tell you what side. The coming from the left, coming from the right. This one, just that value from right to an infinite as I come from the left to infinite. That's a negative, and it wouldn't matter for infinite discontinuity go towards a positive, like you do on the right, a negative infinity we have on the left, where you can actually go to the center. Is graph is never going to stop. I'm never here. That's infinite, but I have to pick some point to write over. Infinite discontinuity and occurs asymptote. The next one, looking at here, it is clearly new, and what it is my graph flowing down here before my A, right at A, down jump up. So at A, all of a sudden, I have a completely different value. So if I'm looking at the limit, that's coming from the right, I'm approaching. But if I'm approaching left, a different value, that value is C. B and C are not the same. Yet from here, I have to make one big And that's what we call those discontinuities. So we have infinite, where when we come from whichever direction from we're going towards infinity, as long as that's on at least direction, that's going to be infinite discontinuity. A jump left or the right will approach values, and I think value B, but all take a jump. This guy, as I roll along from the negative limit, and I roll along from the positive limit, both of them are coming to the same point. They're both going to, they're the same. You know what? If I was dealing with, if it was decorating, if I was dealing with my walls, I'd take back and it would be fixed. Smear there. And doing so, I have removed my so the removal discontinuity because it will small right there. But to what I learned in college. But at least on a whole, no one will see that it's so those removal discontinuities. And on the right, we both have the same value. Let's put these together and kind of identify some discontinuities, some domains, some ranges, some functions, all this wonderful thing. So here we have several graphs. And we're going to first start with the function. We're saying change notation this time. And we're going to determine if the relation is continuous. If not, we're going to talk about the type of discontinuity. So I'm going to zoom out here. I want you to look at 14 through 19. Which of the functions? Which of these are functions? You can think about them as which of these pass the Verline test. Is it a function? It is a function because even though it looks here, you're still you have to zoom. That's not vertical, so that function. What about 15? Is 15 a function? 15 function because I have a circle here, circle. Think of it like all inside. This right in to that one. So it's all function. 6 is a function as well. 17 is a function. We failed the vertical line to number 17. As long as you understand that what's on here is asymptote, and that's not actually part of the graph, it's also a function, just like number 14. Number 18, we're going to talk a lot about guys later on. This is my step. It is a function. Because if I look here, every time I swirl up, go up. Each of those circles will in the open circle. So let's take each through step and let's deal with domain range. And we're going to do this in notation. So what that means is a refresher. When we use these braces, that is set notation. Now we're going to focus, just to make sure that we've seen all of them, on interval notation. Interval notation is about simply talking about intervals. Kind of nice and easy to write. Interval domain for this guy, far left go, is all the way up to negative, all the way to positive infinity. part of my domain. Hops include must write that. When we talk about range, we have a problem here. So my range starts all at the bottom, so it starts all the way at infinity. Up, we have our right here. We start this start up immediately afterwards. Well, it pretty much answers our question as to whether or not this is a function, or if this is continuous. It's not continuous because the continuous only don't about life. It's discontinuous as until so it's infinite continuity equal to 3. Where is that problem? So it's at x equals 3. Don't say x equals 3. What about 15? What is the domain for 15? I'll clarify something to you. If you look at not how I want is that those who stop and not continue going. And that affects how you're going to do your domain. Let's start asking though, is it a function? Do I have to pick up my pen for this? This is not a function. It's not a continuous function right there. 1, 2, 4, 5. I have continuity. So it comes to a value from the left. It looks like it comes value from the right. This is a discontinuity. Discontinuity. It really could to start talking your domain and saying, okay, my domain goes from 1, 2, 5, 6, 8. So a negative. Let's go look much this. 8 negative 5, and I put the union. When you see this, are in both places, that I'm including 5 on one, those two actually get and we did at one domain from negative positive, and everything in between. There's not one point along this line where we are not included. There is a view along line. So what would the range of this be? Look at this. The last does it actually hit negative 3? A parenthesis. 2 pieces. But if you look here, go here. This piece go all the way to here. So if I look at this, and you from negative 3, I'll leave it 8. Any values are possible. Just write this piece and others. They are not graphs on the same graph. When you graph them together, it is one graph. since these are covered, I must show for all linked. Run through 16 and 17. Looking at these, you can continue. Not one, you need to pick your pen to draw, and use interval notation, because I did specify for this interval notation. So it goes infinity. These all have parentheses. Just 17, the domain looks the same. We all the domain here goes from negative to infinity. No, so here goes from negative infinity, which do not include, even though you do not see an open, actually going to that value. We're going to assume that is it. So it goes up to the range, however, is going to negative infinity to infinity. Now 18 and 19. Those continues. Hopefully you quickly know 18 and 19 are not, you have to pick your pen in order to draw them. Let's talk about range first. So I look at this, the main go all the way out to the end. I still lost graph, because I have some graph, lose my graph, somebody to hold it and count that way. So the way that it's into domain, I would make the number line shows. So domain go from infinity, not including 0, to, and then that is notation. This one is your explanation. That is the that is 0 or 2. For the range, D going in the opposite direction. Bottom part apart. Bottom because there's a shell. And I get it. So I'm going to estimate for my range. I don't have value. It's high. Range I get it 0. Union 0. And union to infinity. Instead of say range, for notation, we would say that not be 0. That's but sorry, course. Oh. Now, because these functions are tricky, one depth is a little bit late. Step function is basically saying I put anything I want. So I look here, how you here, then it goes close values. So many numbers, infinity and infinity pi for the very changes. So value here, here. I have a range on each of these. Have them in between. There's nothing here or here. It is only on integers. So for that, this is one that I wouldn't actually write in interval notation. The that is the set of eyes that the it's called double. If you can do other design, but I just do addition. It's not because there is a